Hello everyone, this lecture is about electromagnetic sounding methods and we will discuss about magnetotellurics. So magnetotellurics, or MT, is one non-destructive way to probe the properties of the Earth at depths. And in particular, we will be interested in electric resistivity. The principle is measurements being made at the surface of the Earth, and these measurements are measurements of the electric field and the magnetic field together. One specificity of this method is that the source that will induce magnetic field and current is actually natural, so there is no need for human-triggered sources, like in some of the seismic methods and geoelectrics. Also, the method is driven by electromagnetic waves that travel through the Earth. And these waves reach different depths based on the electrical resistivity of the rocks and on the frequency of the wave. To illustrate that, you have examples of two different MT studies. One applied to a volcanic system. You see the topography here of the volcano, and the depth scale is on the range of several kilometers, -6 here. And on the other side, you have a resistivity map obtained via MT also, but this time it's applied to the lithosphere. So this is a subduction system here, and you see the scale of the map is 120 kilometers depth. So the pioneers of MT basically were mostly active in the 1940s and 1950s. This is Riritake, Tikhonov, and Kanyar. So these are Japanese, Russians, and French scientists that basically wrote the first contribution on the use of induced electromagnetism to probe the interior of the Earth. And basically this development was also driven by the development of electronic devices that allow to measure all these properties. So the sources that are used in MT are basically triggered by variations in the solar wind. So you know that the sun is releasing a stream of particles and which are interacting with the magnetic field of the Earth, but they can also induce if there are massive explosions and fast streaming or increased streaming of particles into the magnetic field. This can induce variation of the magnetic field, and sometimes they can also pierce through and trigger auroras close to the poles. So that's one of the sources of variation of the magnetic field. The second source are lightning storms. So if you have a thunderstorm, this will also trigger some waves, like higher frequency waves, and these waves will be guided between the surface of the Earth and the ionosphere. They will reflect and bounce back. So the interaction of the ionosphere with solar winds and lightning storms trigger changes, temporal variation of the Earth magnetic field. And this triggers telluric currents. Telluric currents are basically EM waves, electromagnetic waves, that travel down towards the center of the Earth. So they go inside the Earth towards the center. And with MT, the idea is to measure the ratio of electrical and magnetic fields to get information on resistivity at depths. And we will discuss how to get there. High frequency wave will allow to sense shallow depths. So shallow depths are here on the scale of 100 meters, while low frequencies reach large depths. Large depths here is on the scale of 100 kilometers. So these are the numbers to remember. The wave periods, which are basically useful for geophysics, are contained between 10 to minus 3 seconds and 10 to 3 seconds. And assuming a resistivity of 20 ohm meters, this corresponds to wavelengths bounded between 400 meters to 500 kilometers. So that's a very large range of wavelength, which can potentially be probed with MT. Another interesting point is the skin effect. So the skin effect is a damping effect of the wave. So the skin effect is basically a reduction of the amplitude of the wave as the wave is going through towards the center of the Earth. So it means basically that there's a decrease of current density with depth. So the current density is the intensity divided by a surface, and it decreases with depth within a conductor. The conductor here is, of course, the Earth. So the current density decreases with depth as with an exponential decay, exponential of minus d. So what you see on this diagram here is a schematic diagram showing the current density versus the depth. And for example, you see a magnitude of 1 at the surface, 0, and then this magnitude, this current density is dropping with depth to a value of 0. And the skin depth is the width for which the value of the current density has dropped to 37% of the surface value. So that's the definition of it. So here in this diagram, it would be a depth of 1. At a depth of 1, you have a value corresponding to 37% of the initial value of 1. So that's the expression of the skin depth, and it's the square root of the ratio of resistivity divided by mu0, the permeability, and omega, the angular frequency. In the second part of the lecture, we will derive this quantity. Now, to give you an idea, this is a sketch of a magnetotelluric station. So, as I told you before, we want to measure several components of the electric field and magnetic field. So, need electrodes to measure the electrical field in here, the plane of the surface, the two dimensions, Ex and Ey. A magnetometer with 3 components is required to measure the magnetic field in the 3 dimensions. So these are these guys here. An acquisition unit is necessary to record the measurement. A GPS will give you the position of your station, and of course a battery to feed the acquisition unit. And then one can form a network also of magnetotelluric stations. So this is just an example of 2 stations at 2 different places on the Earth's surface. You see different sources of electromagnetic wave, lightning and sun. So there are time variation in magnetic field, and this will allow to measure the resistivity structure inside the Earth at different locations. Here's an example of a magnetometer. So this is called a flux gate magnetometer. The specificity of this magnetometer is that it can record the three components of the magnetic field in a single device. And it allows to cover a long range of periods. So from 1 second to 10 days. So with 1 second, of course, you will probe high frequency, so shallow depths, but with 10 days, you will reach very long wavelengths and probe structure in the deeper part of the Earth. This shows you in practice how to set up the thing. So basically you need to dig holes and bury the electrodes. So you need to form the network of electrodes to measure the electrical field and the two components of it. And you need to bury magnetometers to measure the magnetic field in the 3-dimension below the station. Sometimes for your safety, you will also need to be in company of people who can defend you if dangerous animals or humans want to attack or steal your equipment. This picture here shows you the cascading effect of induction. So you see here an induced tension that induces a current, and this current, now you know that it induces also a magnetic field. So that's basically the idea, that there is an induction loop which is triggered. And this happens in a medium, which is the subsurface, and which has a specific resistivity rho. Now the data, with all this equipment, the data will be basically time series for a given station. And in the time series, you see here, for example, two components of the electrical field, Ex, Ey, and the three components of the magnetic field. And on this example, you see a comparison of recordings of different stations. So the different lines correspond to different locations in the Earth. And if you zoom, you see differences between these different locations, because they're, of course, located at different places. So that's it for the first part of the lecture. So magnetotellurics is a method based on electromagnetics. It's a passive monitoring method, so the sources are natural. And the main equipment which is required are magnetometers and electrodes. And the data which will be acquired are surface electric field, Ex, Ey, two components, and the 3D magnetic field, Bx, By, and Bz.